Today's lesson is using equation to solve word problems. The grade 9 word problems are specifically designed to be able to be handled by the math we have so far. So if they seem a little weird or who would ever actually do word problems like this with these equations, that might actually be true. We're just practicing for later grades. So just to play along here, we're getting you ready for the later stuff. So for each of the following problems, create an equation to model the situation and use the equation to solve the problem. So we're setting up a plan where you'll be able to do tougher word problems later. So follow along, and it's important that you do each of these things each time to be able to do word problems like this. We want a let statement. Now the let statement makes a decision about what the unknown is in the question. So when you first read a word problem, don't get too excited about understanding everything that's going on in the word problem. Just read the problem trying to find out what's the unknown. What are we trying to find here? So let me read it again. It says 15 more than 3 times a number is 27. What is the number? So the first time through you read it, you might find a lot of things confusing, but the one thing that's not confusing is what are we trying to find, and we're trying to find out what this number is. And so our let statement lays that out for us. We say let n be the unknown number. And if the first time you read any word problem ever in math, all you accomplish is going, what's the unknown and what letter am I going to use to represent the unknown? You've had a highly successful first run at reading the question. Then the second time the question, you try to understand where does that number fit into the question. And this says 15 more than 3 times a number is 27. Well, I've got some idea of what this equation might look like then, because I need something that has 15 more in there. And I got to do 3 times the number, and that's all got to come out to 27. Let's talk about the 3 times the number first, because that's the first part that really talks about the number that I'm looking for. It says you have to go 3 times that number, and I said let n be the unknown number. This leads me to go, oh, 3 times a number. So I wrote 3n, because my number that they're talking about is going to be n. I don't know what that number is, but I do know they want to go 3 times that number. Next, they said we want 15 more than that. So 3 times the number, and we want 15 more, so I got to go plus 15. That's now 3 times the number plus 15. And they said that's all got to come out to be 27. So 3 times the number plus 15 has to come out to 27. That's a fairly simple example to walk through, and maybe the equation popped in your head when you first saw it, but I'm trying to give you weapons to handle tougher situations. Well, the rest of this is just the equation solving for the rest of the chapter. If we want to do the opposite of add 15, then we've got to subtract 15 from both sides. And maybe you don't even write that step now. Maybe you write this step and you just go, okay, when I move add 15 over, it becomes subtract 15. It's okay if you write the step. I like the step, but if you're skipping over that, I'm sort of saying that's okay. And then 27 minus 15 is 12. Divide both sides by 3, and I get n equals 4. Now, the other thing a word problem needs is a therefore statement at the end. The idea being, if a question's asked in words, it should be answered in words, not with algebra. We use the algebra to get the answer, but the answer should come back in words like the question was. Therefore, the number is 4. Let me just put some numbers in the column here so you understand the steps to solving word problems. 1, we need a let statement. 2, we need an equation. 3, we need to solve the equation. And 4, we need a therefore statement. Those 4 steps should be in any kind of word problem. Well, the rest of the lesson is just the same, just some new situations, and they get tougher and tougher. Like really tough. There's a really tough one at the end that I want to lay out for you. So let's just scroll up to the next problem here. This one says the length of a rectangle is 5 centimeters greater than the width. Well, a situation like this, as soon as they mention a rectangle, I know I said read for the unknown, but whenever you get a word problem that's got a shape in it, I think you should immediately draw the shape. And they said the length of the rectangle is 5 centimeters greater than its width. So if the perimeter of the rectangle is 148, determine the length and width. So this is the unknowns. Determine the length. So what I'm going to say is let W be the width. That's the unknown. So I'm going to put W on my rectangle there. I know some people say, well, W's the left or right distance, not the up-down distance, but it doesn't really matter. I mean, width is whatever you want it to be. So let W be the width. Now, a lot of people then would say, let L be the length. And you could do that, but you're causing yourself sort of a problem here if you make L the length. And in geometry problems like this, we want to avoid using extra variables if we don't have to, because it makes the question a lot more complicated. Because they told us something about the length. The length is 5 centimeters greater than the width. So what I'm going to say is let the length be W plus 5. So when I put it on my rectangle here, this length is W plus 5. What's very nice about that is I haven't introduced a new variable. It's all W's now. And you'll see when I make the equation why that's so handy to stick to only one variable. So if they give you other information about one of the sides that incorporates the sides you already have, don't try and introduce an extra variable here. It says the perimeter of the rectangle is 148. So if I want the perimeter, well, I've got a beautiful rectangle here. The picture is so handy here. It shows all the sides there. And it says the perimeter has to be 148. Well, you have to know something about perimeter. And we don't ask too much geometry in this chapter, but one thing we do ask is that you know how to find the perimeter of a rectangle. And the perimeter of a rectangle is you just add up the sides. And so if I'm going to add up the sides here, I get W plus 5 plus W plus W plus 5. If you've got a shortcut to doing all that, that's great. And that perimeter's got to come out to 148. There, now I have an equation I can use to find the perimeter. I'm going to collect some like terms here. I see 4W's plus 10. I'm going to subtract 10 from both sides. I get 4W equals 138. And then finally, I'm going to divide by 4. Punch that in my calculator. I get 34.5. Now, this question said determine the length and the width. So if I want the length, the width would be 34.5 centimeters, and the length would be, well, how do I get the length? Well, I got several options of where to find the length. I could look back at my rectangle and say, oh, to get the lengths, I just add 5 to the width. Or I could look up here and go, let the length be W plus 5. Or even the original question says the length is 5 centimeters greater than the width. Any of those spots tell us, oh, I need a 5 centimeter bigger number there, and so the length would be 39.5 centimeters. I put the therefore statements up there, even though I left a space for it down there. Okay, so geometry problems really draw the picture. And another trick I'm trying to show you here is don't introduce extra variables unless you absolutely have to, because they can cause other problems. If you can do something like this and say, oh, the length is W plus 5, it incorporates the measurement you already have there. Okay, example 3. A teacher opened 4 new boxes of pencils. She placed 3 pencils on each desk with 7 pencils left over. If each box has 28 pencils, how many desks were there? This is the type of word problem that drives people bananas, because there's so much going on. And the first time you read through it, your brain can sort of explode and go, well, what am I supposed to do here? So I want to simplify things down and just go through and say, well, at the end it said, how many desks were there? And that gets me well on my way to doing the first step in these questions. Because look, back in here, what I said is there should be 4 steps to these questions. State the unknown, do a let statement. Step 2, make an equation. Step 3, solve the equation. And step 4, a therefore statement. Those steps are all there. Were those steps here the second time? Step 1, let statement. Step 2, make an equation. Step 3, solve the equation. And step 4, a therefore statement. We should see that in all word problems. So even if you're not sure exactly how to proceed, we can at least do step 1 here. Step 1 is the let statement. Let D be the number of desks. I use D because that's a convenient variable to use. People get addicted to X, and that's fine, but I like using variables that really tell me about what I'm actually looking for. Now then, come up with an equation. There's all these desks in the room, and let's talk about how those desks were used. The only way the desks were used is she put 3 pencils on each desk. So how many pencils were put on the desks? If 3 pencils were put on each desk, Well, 3 times the number of desks. And I've used D for the number of desks. So the total number of pencils she put out in the room was 3 times the number of desks. Almost. She said she has 7 pencils left over. So the total number of pencils is 3D plus the 7 left over. 3 pencils for each desk plus 7 left over. What does that got to come out to? How many pencils did she have? She said she had, in each box, there was 28 pencils, and there was 4 boxes. So she has 4 times 28 pencils to begin with. So how many did she put on the desks? 3D plus 20, plus, she put 3D on the desks. She has 7 left over. Where did those pencils come from? 4 boxes of 28. The rest is just the math we've been doing in this chapter. 4 times 28 is 112. Subtract 7 from both sides. Divide both sides by 3. And I get 35. What is 35? Okay, it's easy to get confused in all this. What was the 35? And that's why this let statement is so important. You might be like, oh, why do we need a let statement? It's for when you're done all the algebra, you can look back and go, what was I doing here? What was I trying to solve for? I found D equals 35, and that tells me it's the number of desks. That helps me do my therefore statement. Therefore, there were 35 desks. Step 2 was make an equation. Step 3 was solve the equation. Step 4 was put a therefore statement. Listen, I'm not trying to imply these are easy. They're not. Every situation is different. But the steps are what's important here, is that you should make a let statement, think about the situation, and try to use the variable you created to create an equation for the situation. And once you do that, the rest of the skills from the chapter start to kick in. 2 more examples to go. A t-shirt was regularly priced at $9. Lucas purchased the t-shirt for $6.75. What percentage was taken off? Now, this is a little bit confusing question, but the important thing is the unknowns. Let P be the percentage. And there's a little problem in this question that we'll deal with at the end, but I'll just put let P be the percentage, and we'll deal with that then. So what happened was they took $9 and they multiplied it by some percentage and ended up with $6.75. And we want to know what that percentage is. If you really know your percents, you might see a problem looming. I don't want you to worry about that problem just yet. I'm going to deal with it at the end. For now, you take $9, you multiply it by some percentage, and you get $6.75. So to get the percentage, I take $6.75 and I divide it by 9. I get the percentage here as 0.75, which is, I should be thinking when I see 0.75, that's 75%. But what you have to ask yourself is, was 75% taken off the price? I mean, if you take 75% off a price, will you go from 9 to 675? I mean, if you take 50% of off a price, you'd be down to 450. So 75% off would be much larger than that. So it wasn't 75% that was taken off. You've got to think for a second and say, I got 75% of the price. So this 675 was 75% of the price. So what was percentage was taken off? Therefore, 25% was taken off, giving 75% of the price. So a little bit of thinking there at the end with percentages. And percentages are like that. You always have to do a little bit of thinking with percentages at the end to see what was going on. Did I do my 4 steps? Let P be the percentage. 2, made an equation. 3, solve the equation. And 4, a therefore statement. But there was a little extra in this one. There's a little bit of thinking that had to go on to answer the question. And that's why we try to make you do a word answer, because the word answer forces you to look back at the original question and really think about it for a second and make sure you've got the right answer. Okay, that's all the type of word problems that you're really, that's the highest level of word problem you'll probably see on an assignment or a test in this chapter. But I do want to go a step farther. So just to really see a word problem that's really got some torque to it, a really upper level word problem. Example 5. If Ryan takes 2 hours to paint a room, it takes Ryan 2 hours to paint a room. It takes Maria 3 hours to paint the same room. If Ryan and Maria work together, how long will it take them to paint a room? This is the kind of problem that algebra was invented for, because these are not easy problems to do. I mean, it's easy. Lots of people immediately think, oh, is it 2 plus 3? Just add the hours together and give 5 hours? And there's no way that can be right. There's no way it can be 5 hours that's going to take them to paint the room, because Ryan can do it in 2 hours by himself. So there's no way it's going to take 5 hours total. So then some people take the two numbers and they add them together and divide by 2 and go, oh, it's going to be 2.5. Well, there's no way that can be right either. I mean, the answer has to be smaller than 2, and there's no easy way to know what to do with these numbers. And the answer isn't 3 minus 2. So we've really got to think about this situation and come up with a new method of thinking to come up with a solution. There are plenty of ways to do this, and your textbook presents a way to do it, and you should definitely check that textbook version out as well. I'm going to show another way to think about this problem that really helps. All I'm going to say is, in my thought bubble here, I'm going to go, what happens in 1 hour? 1 hour is a good time to think about because it's a nice whole number, and it's easy to think about what happens in 1 hour. And my let statement is going to be let x be how long it takes to paint the room together. That's the unknown in the situation. So let's talk about what's happened in 1 hour. How much of the room has Ryan painted in 1 hour? It usually takes him 2 hours to paint a room. In 1 hour, he'll have done 1/2 of the job. Now, Maria, how much of the room has she done in 1 hour? It usually takes her 3 hours to paint the room, so in 1 hour, she'll have done 1/3 of the room. That total fraction has to add up to the total amount of the job they've done. What fraction of the job have they done in 1 hour? Together, it takes them X hours. So in 1 hour, they'll have completed 1/x of the job. For instance, if it would take them 5 hours to paint the room together, this would be 1/5. If it was 10 hours to paint the room together, this would be 1/10. That takes a lot of thought. That's an upper level equation. If you get that the first time I write that out, oh, I'm so proud of you, because that is very, very difficult. You may have to rewind the video and watch it all again to go, what is going on here? Basically what I did is I said, okay, this is the fraction Ryan does in 1 hour. And this is the fraction Maria does in 1 hour. And that has to add to the fraction together in 1 hour. After watching that part of the video a few times, it really caused you a problem. Also, take a look at what the textbook presents, because it represents another way to handle this situation. Because the way I've put it together, this is a tough equation to solve. I do want you to see how to solve an equation like this, because I do want you to see where this is going, that the equation solving can become a little more than we've seen so far. So let me go through solving this equation, and I hope I'm not going to do anything that actually blows your mind too much in solving the equation. What I'm going to do on the left-hand side is get a common denominator. So this is 3/6, and this is 2/6. I'm not going to do anything over here. This 1/x is really, really scary, and I'm not going to deal with it just yet. 3/6 plus 2/6 is 5/6, and that has to come out to 1/x. Now, here's the big move, and I hope this doesn't blow your mind. One of the things we've been teaching in the chapter is that you can do anything you want to an equation as long as you do the same thing to both sides. We could subtract 5 as long as we did it to both sides. We could divide by 3 as long as we did it to both sides. And here's one more trick, and there's many more coming in future grades, but here's one more trick you can do to both sides. You can flip both sides. You decide you want to flip both fractions, you can, and that's what I'm going to do here. I'm going to switch this to 6/5 equals x over 1. And what is x divided by 1? Just x. Now, listen, it doesn't, you really want to get this into mixed numbers. 1 1/5. Therefore, it takes them 1 1/5 hour to do the work together. Now that is a hyper scary word problem. I don't want you to get too intimidated by that. We wouldn't put that on a test or assignment. That's really reaching up another level so you can see where we're going with all this. Because sometimes at the end of these word problems, you're left with this impression that equations aren't needed to solve these things. I can just think them out. And that's probably true for a lot of the equations we're going to do. But we really want to practice these methods on simple word problems so that we can get ready for stuff like this in future grades. That is quite a problem. In fact, it's a great problem to ask friends and family about to see what they think when you first just state the problem and see if they can come up with an answer. And actually, it's a great problem to do a bunch of different ways. So it's got lots of torque to it. Okay, listen, the word problems in the homework, there's some easy ones and there's some tough ones. These things take practice. Please, please, please go through the word problems with a strong mind. And I don't mean strong mind like you're going to be so smart and get all the questions in 2 seconds. I mean strong like when it doesn't go well and you have trouble with the word problems and the answers you get don't match up with the back of the book, we don't freak out. We take a look at them again. We ask a friend. We ask a teacher. We contact somebody and just work our way through it and learn about these word problems because I'm telling you, it's going to matter. Despite what you might see on social media and on movies and TV shows, being able to do these kind of questions really matters. We really need people in this world who can do these type of equations. And it just is practice. It's not a gift that people are born with. It takes practice. So practice these, please. Any problems? Get in touch. We're here to help you.